Good morning and thanks for tuning in. Today's lesson is section 1.3, day 2, evaluating limits analytically. This deals more with evaluating trigonometric functions. Just like we have in the past, we're going to use direct substitution at points where the functions are defined, at points within their domain. So you'll see in A through F we have the limits of the different trigonometric functions just using direct substitution. We're now going to apply what we learned on the last slide and evaluate these trigonometric limits using direct substitution. The first problem says find the limit as x approaches 0 of tangent of x. So we're simply going to plug in 0 for x. And what that means is tangent is sine over cosine, so we have sine of 0 over cosine of 0. And we know that sine of 0, if we use our unit circle, the value is 0. Cosine of 0 on our unit circle is 1. So our limit, as x approaches 0, of tangent x is 0. Our next problem is asking us to find the limit, as x approaches pi, of x cosine x. We learned on Friday that when we're dealing with limits involving a product, we can split those limits up. So we can rewrite this as the limit as x approaches pi of x times the limit as x approaches pi of cosine x. Through direct substitution, we're just simply going to plug in pi in for x. So the limit as x approaches pi of x is simply going to be pi times the limit as x approaches pi of cosine x is going to be cosine of pi. Cosine of pi has a value of -1 on our unit circle, so our answer is going to be pi times -1, which is negative pi. In C we have the limit as x approaches 0 of sine squared x. We're going to directly substitute, and we're going to rewrite this squared in a slightly different way. So when we use our direct substitution, we have sine of 0, and when our square is right here between the trigonometric name and the actual value, okay, that means the whole trig function is being squared. So we can rewrite it as sine 0 quantity squared. Sine of 0 is simply 0, and if I square 0, I get 0. D says find the limit as t approaches pi of 3 plus sine t all over 1 minus cosine t. Again, we can use our properties of limits to split this up. So we can rewrite it as the limit as t approaches pi of 3 plus the limit as t approaches pi of sine t over the limit as t approaches pi of 1 minus the limit as t approaches pi of cosine t. As I begin to evaluate, the limit as t approaches pi of a constant 3 is just going to remain 3. Plus, plug pi in for t, so we have sine pi over the limit as t approaches pi of 1 is going to be 1 minus, plug pi in, cosine pi. We can now go to our unit circle, figure out these values of sine pi and cosine pi. So we end up with 3 plus sine of pi is 0 over 1 minus cosine of pi is negative 1. Two negatives here make a positive. We clean it up and we have 3 halves. Our last problem before moving into the squeeze theorem is the limit as x approaches 7 of secant pi x over 6. Let's simply take our 7, plug it in for x, and go from there. So we now have secant of 7 pi over 6. So we need to evaluate that to actually see what the limit is. We know that secant is the reciprocal of cosine. So let's find cosine of 7 pi over 6 on our unit circle. When we do that, we find that it's negative square root of 3 over 2. But cosine is the reciprocal of secant. So now we need to flip it around. We have 2 over the square root of 3, and it is negative, but we can't have that radical in the denominator, so we multiply the numerator and denominator by the square root of 3, and we end up with negative 2 square root of 3 over 3 is our limit. Next up we have the squeeze theorem. At first it looks a little complicated, but let's break it down. It says if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself, and the limit as x approaches c of h of x is equal to the limit as x approaches c of g of x, then it means that the limit as x approaches c of f of x is also L, which was the same as the limit of h of x and g of x. Reason being, our f of x function is between h of x and g of x. So if the limit of h of x is the same as the limit of g of x, and f of x is between h of x and g of x, then they all have equal limits. Here's an example where we can use the squeeze theorem. It says, using the graphing calculator, graph f of x equals sine x over x, y equals 1, and y equals cosine x. Then use the squeeze theorem to find the limit as x approaches 0 of f of x. Now, the reason we can't just use direct substitution in our function f of x as x approaches 0 is because I get 0 in my denominator, which we know can't happen. So let's take a look at our graph. Looking at our graph, you'll see that all of our functions pretty much meet at the same point. Okay? And our f of x function is between our two other functions, which are y equals 1 and y equals cosine x. Therefore, we can come to the conclusion that if the limit of the other two functions are the same, the third will also be the same, which is 1. Here we have the beginning of the memorization of what we need to know with limits. There are two special trigonometric limits that we must memorize. The first is the limit as x approaches 0 of sine x over x is 1, which we just kind of saw using the squeeze theorem. The second limit that we need to memorize is the limit as x approaches 0 of 1 minus cosine x over x is 0. It's also important to note that the reciprocal of a is also 1. I'm also going to add in one other that you should memorize, and it's the limit as x approaches 0, tangent x over x equals 1. Okay, so these are three limits that you can evaluate mentally through your memorization without showing any work. Okay, you need to memorize these because these are used to find the limits that involve trig functions and have that form of 0 over 0 when you use your direct substitution. Okay, so you can use these because if you get stuck with a trig limit, you can try to rewrite it as one of these special trig functions or trig limits with fancy algebra, as we call it. We're now going to do a couple example problems dealing with these special limits that you should have memorized. Also included in these problems is the properties that we discussed on Friday. So what we can do, because of our properties, we have this 4 inside here. The limit as x approaches 0 of sine 4x over x. We can pull this 4 out front, rewrite it as 4 times the limit as x approaches 0 of sine x over x. So now using our rewriting with our properties in algebra, we know that the limit as x approaches 0 of sine x over x is 1. So 4 times 1 gives us our answer of 4. Next up, we have the limit as x approaches 0 of 3 minus 3 cosine x over 9x. First thing you should think of is when in doubt, factor out. We can factor a 3 out of our numerator. So let's rewrite the limit as x approaches 0 of 3 times 1 minus cosine x over 9x. We can now take our leading coefficient of 3 and 9, pull both of those out front. So we now have 3/9 times the limit as x approaches 0 of 1 minus cosine x over x. This then becomes 1/3, or 3/9, and the limit as x approaches 0 of 1 minus cosine x over x is one of those special limits that we need to memorize, and the value of that limit is 0. So our answer is 0. Next up, we have the limit as x approaches 0 of 2 tangent x over 5x. Let's take both of our leading coefficients, bring them out front. 2/5 times the limit as x approaches 0 of tangent x over x. Here's another one of our special limits that we have to memorize. So our answer is then 2/5 times 1, which is 2/5. We're going to continue to use our fancy algebra in order to try to get to these special trigonometric limits that we know by memorization. So here, what we can do, we have the limit as x approaches 0 of 8 sine 6x all over x. Now you've seen us pull out our leading coefficient, and you also saw us pull out the leading coefficient of inside our function operator. We're going to do both of that. So the 8 times 6 is 48. So technically we have 48 times the limit as x approaches 0 of sine x over x. We know that the limit as x approaches 0 of sine x over x is 1. So our answer, 48 times 1, which is equal to 48. Just like the last problem, let's pull out the 2, let's pull out the 5, bring them out front. So we now have 2/5 times the limit as x approaches 0 of sine x over x. Here we have one of our special limits again. The value of that limit is 1, so 2/5 times 1 gives us our answer of 2/5. Here in f we have the limit as x approaches pi over 4 of tangent 5x over 4x. Now what you'll notice is that we're no longer approaching 0. Okay, so all the other problems, if I plugged in 0, I would have 0 in the denominator, which I can't have. So let's just plug in the pi over 4. There's no need to make it any more difficult than it needs to be. So let's use our direct substitution. So we have tangent of 5 pi over 4 divided by 4 times pi over 4. So you have the tangent of 5 pi over 4 over, those 4's cancel, over pi. When I go to my unit circle to evaluate the tangent of 5 pi over 4, we get 1, so the answer is 1 over pi, which is a legitimate answer because pi is a constant, it represents a number. Lastly, we have 4 pretty quick problems in which we're going to utilize our properties in order to evaluate our limits. So we're told that the limit as x approaches c of f of x is equal to 3, and the limit as x approaches c of g of x is equal to 2/3. So we're going to use our properties to evaluate first the limit as x approaches c of f of x minus 2g of x. First thing we can do is we can split these limits apart to be the limit as x approaches c of f of x minus the limit as x approaches c of 2 times g of x. We're not done with our properties yet because we can pull that 2 out. So we now have the limit of f of x as x approaches c minus 2 times the limit as x approaches c of g of x. So it said earlier in the problem that the limit as x approaches c of f of x is equal to 3 minus 2 times the limit as x approaches c of g of x is equal to 2/3. Now we just need to follow PEMDAS. So we have 3 minus 4/3, which is going to give me 5/3. Because 3 is technically 9/3. 9/3 minus 4/3 gives us 5/3. Next in B, it says the limit as x approaches c of f of x squared. So all we have to do, figure out what our limit as x approaches c of f of x is and square it. It said at the beginning of the problem that our limit as x approaches c of f of x is 3. So let's take 3 and square it. So our answer is 9. Okay, so we have 2 more problems. C says, find the limit as x approaches c of f of x times g of x. Our properties say we can split up a product to 2 separate limits. So the limit as x approaches c of f of x times the limit, let's try this again, times the limit as x approaches c of g of x. Okay, this limit value is equal to 3, as stated at the beginning of the problems, times this limit value, as stated at the beginning, is 2/3, 3 times 2/3 gives us an answer of 2. And our very last problem of the weekend, we have D. Find the limit as x approaches c of g of x over 4. Take that, move it out front as our leading coefficient. Because the 4 is in the denominator, that means we have 1/4 times the limit as x approaches c of g of x. The limit as x approaches c of g of x is actually equal to 2/3, so we substitute it in. 1/4 times 2/3. We can do some cross canceling, and we get 1/6. Thank you for taking the time to do this flipped classroom assignment over your long weekend. Just a reminder, Tuesday in class you'll use what you learned in this lesson in order to complete homework 1-3, day 2. You should also then work on review 1-2 to 1-3. Everything's in your packet, and your quiz will be on Thursday. Okay, have a good day on Tuesday, and I will see you when I'm back on Wednesday. Have a good weekend.